Hello, everyone. Today we have back-to-back videos. So we just finished part one of the search insert position for LeetCode, where we performed it in time complexity of linear time complexity. And that's because we used linear search. Strongly recommend watching this video. This one was really fun, being able to use this tool. So this is the tool that we're going to be looking at to be able to kind of describe how binary search works. So there are other visual tools that exist out there on the internet, but this is just one I kind of coded out with the function. Using IO_manip. It's not very impressive, to be honest. It's a lot of hard coding, if I say so myself, but it's pretty handy in the sense that it gives us a lot of information to be able to kind of step through. So that being said, let's go ahead and get to it, kind of understand what the problem was asking us. If you haven't watched part one, I'm just going to do a quick review. And this is essentially where we're going to be given a vector of integers. So this kind of like a list here, and we're going to be given a key, also known as a target. And we want to find if that target exists within our vector. We're going to go ahead and return the index where we found it. So notice that this key exists within our list, specifically at index 2. So that's why we return index 2. Now, what if it doesn't exist in there? If it doesn't exist in there, there's a lot of functions that say if you can't find your key within a vector, it'll return -1. That's not what this is asking. This is asking if it doesn't exist in there, go ahead and tell me where it should be inserted in order to remain in order to remain as an ordered list. So notice here, all of these are going to be ordered lists that were being provided, and we're going to be given keys. So in this case, if I have the key 2, at what index should I insert this so that it remains ordered? Should I insert this at the end? No, right? That doesn't make any sense. If I insert it at the beginning, it doesn't make any sense. It gets out of order. I should insert it right at index 1. I should insert it right in front of this 3 so that it becomes 1, 2, 3, 5, 6. So notice I should insert it at index 1. That's why the output is 1. It's essentially saying that we're going to go ahead and insert it at that location. The same thing goes for here. Here, my target is 7. Notice my target or my key is not within my vector. So where should I insert it? At what index? I should insert it at index 4. So that's why we're going to go ahead and insert it at the very, very end. So once again, the previous example showed how we can do this with linear search. The actual code to do it with linear search is here. I'm not going to go over it in this video just because in the previous video we already did that. But this video is much more exciting, I'll be honest, just because we're going to be able to go through binary search. So for binary search, let's get rid of these notes and let's go ahead and provide the notes for this video. So in order to go ahead and do that, let me go ahead and paste that there. Bear with me, please. What we're going to do is we're going to discuss kind of the logic for it. Now, the reason why I'm not going over the example of how to do it, notice I kind of actually do it here. We'll kind of roughly look at it here, but I kind of prefer to use this visualization tool. It's just that this doesn't look as nice as if I were to go ahead and just print out all the steps. But enough about that. Let's go ahead and discuss the logic. So for binary search, what we're doing, the kind of high-level view is we go ahead and take the middle element and we see if that's our value. So let's say, for example, I had 1,000. Like let's say I had a size 1,000 vector list or vector, right? So I have 1,000 things in there. So you can imagine that, or let's say 1,001, just to kind of make the math a little bit clean. You can imagine that I have 500 on the left, 1 in the middle, and 500 on the right. Now, what this approach does is, in order for this to work, the list you're given must be ordered. It's very, very important that the list you're given must be ordered. If it's not ordered, you have to order it. Now, whenever you order something, whenever you sort something, so sort, that's not free. That costs time. And specifically with regards to time complexity, that's n-log_n. So just notice that that's kind of expensive. It's not as expensive as n², but it's still pretty costly. So in this case, if you're given for free a sorted list, then that's perfect. That got rid of the sorting issue. And now once you have a sorted list, you can perform binary search. Binary search, just to kind of give you a clue, it's going to go ahead and be log_n. So it's technically going to be log2 based on, or log base 2, which means that every time we search through our list, we're going to cut away half of it. So let's say I have 1,000, roughly 1,000. Next time I'm going to go ahead and after one search, I'm going to have 500 left. And if I don't find it again, I'm going to have 250 and then 125 and then 62. and so forth and so forth. So you can see every time we're cutting it in half, that's so much faster than using a linear approach. Because in a linear approach, I'd have to do this 1,001 times. I have to go through every single value. In a binary search approach, I'm cutting off the fat half at a time. It's really easy. So what you do is you go to the middle element and you check, is that the value that I was searching for? If it is, great. You go ahead and just say that, perfect, I go ahead and return that index, looks good. If not, I have to think, is my key smaller or is my key bigger? The key that I'm looking for in this list. If the key is smaller, then I should just focus on these right here, these left 500. And I can get rid of all these, just like that. And just like that in one iteration, I just got rid of half the size. That's very, very impressive. Very impressive property. Now, if the key is bigger, I know it should be on this right-hand side, right? I know that it should be on this right-hand side. So I'm going to go ahead and get rid of all these values on the left, including the middle element, just because we've already searched that that's not our value. So now we're left with half again. So essentially, it becomes a binary search, binary decision where, well, there's technically 3 possible paths. If you find the value, you're done, right? If you don't find the value, then if it's smaller, go to the left because it should be on your left. If it's bigger, go to your right because it should be on your right. And the way we kind of facilitate all this logic is using quote unquote pointers. We're going to use 3 pointers. We're going to use a left pointer, we're going to use a right pointer, and then we're going to use a middle pointer. So these are not pointers like in my previous video with like actual like linked lists and a dynamic memory allocation. These are just referred to as indices, but I'm just using the logic, the terminology that kind of gets thrown around. So we're going to use 3 indices or 3 pointers, so to speak. So now that we kind of understand that at a high level, let's go ahead and actually go through the instructions, and then we'll see it in action. So here, binary search, the first thing we need to do is we need to set up a left pointer. So that's going to start at index 0. So at the very left of my list, so this would be my left pointer, or index 0. That's the element that it would refer to, but it's going to be an index, remember. Then you're going to have a right pointer, and that's going to go to the last index. So that's going to be here. It's going to be your size -1. And we're going to continue. So this whole logic is valid while your left pointer is less than or equal to your right. So if your left pointer is still on the left side and your right pointer is still on the right, that's still valid, right? You haven't kind of crossed lines at any point. If they're right on top of each other, so just imagine if you have a vector with only one value, then your left pointer is the same as your right pointer. That's still valid. You can still perform that comparison. It's just that your middle pointer is technically going to be right there as well. So your left, right, and middle are all going to be stacked on top of each other. We'll see an example of that as in right here. So here's the left, middle, and right all stacked on top of each other. This is still valid. I can keep searching. It's only when they cross that your left is now on the right side and your right is now on the left side. That's where you stop. That's where you don't keep going. I love the fact that we can kind of visualize it here. Sorry, I can't. It's kind of nice. So just because doing it this way would have been really rough. So if you do enjoy this, please like, share, and subscribe. Just because I did have a lot of fun, but yeah, no, actually, I just have a lot of fun doing this. But if you do enjoy it, just go ahead and I would appreciate if you could like, share, and subscribe. But enough about that. Let's go ahead and continue. So what we want to do is now that we have our left pointer, right pointer, and we have our condition, while our left is on our less than or equal to my right, continue doing this. What are the steps that we want to do? Well, first off, we use the left and the right pointer to calculate the mid index. We'll talk about exactly what that math is, but it's essentially going to be right here. Actually, let's go ahead and discuss it really quickly. So let's say I had a left index, or let's say I had a left index of 17 and a right index of 25. What's in between here? What's the middle value? So how would you solve that? The way you would solve that is you would do the right minus the left. So 25 minus 17. You go ahead and divide that by 2. And then you'd go ahead and add the offset. Okay, so add the beginning, the left pointer, essentially what's 17. And so let's see if this checks out. So if you just do this part, this is the offset from the beginning. Okay, so don't get confused. Don't only do this, you also have to make sure to add your offset. So if I do 25 minus 17, I get 8. So here's 8. If I do 8 divided by 2, that's 4. Keep in mind this is integer division, so just know if you get an odd number, it's not going to give you a decimal when you divide by 2. It's going to give you a whole number. Anyways, here's 4 plus 17, that gives you 21. And lo and behold, you'll see that that's exactly, that's going to be roughly in the middle between these two values. If you don't have that 17, we're just going to be left with, right? If we were to get rid of this, we're just going to be left with 4. And that's not the index you want to be searching at. That's how you get out of bounds array issues. So make sure that you go ahead and add your offset, which is your beginning, or you could subtract it from your higher value, your right pointer. So you either add your left pointer or subtract from your right pointer once you do that whole division. But that's really the formula. So notice that every time we go into this loop, we need to calculate the mid index based off the left and right pointers, as we saw. If the middle element matches the target, we're good. Exactly like that example with the 1001 elements. If we found it, just go ahead and return that index. You're done. But the issue becomes if my key or my target is smaller. If my target is smaller, it should be on the smaller value side, which is the left side, because it's sorted in ascending order. Assuming it's sorted in ascending order. It could also be in descending order, but just don't do it that way. You could do it that way, but then you just have to reverse a little bit of the logic. But anyways, assuming ascending order, if it's smaller, we're going to check the left side. So what we want to do is we want to keep the left pointer on the left. We're just going to move the right pointer to the left of mid. So whenever we want to move to the left side, we need to shift the right pointer over to the left-hand side, okay, to the left of mid. And we exclude mid because we've already considered it, so we don't need to have it. And this shrinks our boundary, right? So this cuts it in half. The next idea is if our target is greater or our key is greater, then that's when we know that our target is going to be on the greater value side, which is the right side. So in order to do that, we don't have to move our right pointer. Our right pointer is already on the right boundary. We want to move our left pointer to get rid of all those smaller values. So we want to move our left pointer past the mid index, right? And that's really it. So we keep repeating this, until eventually the left is actually on the right side and the right is on the left side, which means we never found it. So, I mean, you could possibly have found it, but let's say if we never found it, then once again, the left is on the right and then the right is going to be on the left. And at that point, we're going to return an index. So you have two options what to return. You can either return the left pointer or the right pointer plus 1. Now this part, honestly, it confused me why this always works. It just kind of works out with the logic or the way we see it. And it's really because the left pointer is going to be 1 greater than the right pointer, right? So, and then the right pointer is always going to be 1 less than the left pointer once they cross over, just according to this movement that we're performing. Now, I didn't kind of know why we use the left pointer, but that's okay. We're going to visualize it in our example. So let's go ahead and turn our attention finally over to our visualization tool. So hopefully, if you're kind of waiting for this from part 1, thank you for your patience. I'm pretty excited to kind of take a look at it. So let's go ahead and take a look at this example. So if I have the values 1, 3, 5, 6, let's stick these in here, 1, 3, 5, 6. And my target was 5, I believe. Yeah, I should get an output of 2, right? So let's go ahead and have that. Let's go ahead and run it. So notice our target is 5. And let's kind of explain what's going on here. Just for kind of, just to make things convenient, I went ahead and printed out the formula. And this is going to be, so this is our formula. Middle index is equal to left pointer minus right pointer divided by 2, and then plus the left pointer. That's just so that you can remember that as we're going through this, so we can calculate it, or you can calculate it as you kind of go through these steps. But it'll print out exactly where it is for us. We'll do this like the first time, but then afterwards we'll assume that this is working as it should. So here's step 1 of binary search. Step 1 of binary search. So we have printed out the steps. These are going to be the indices of our list, and this is the actual list values. So the list values were 1, 3, 5, 6, and I ordered it so that it's the row below is going to be the left pointer, the row below that is going to be the mid pointer, and the row below that is going to be the right pointer. So it's always going to be ordered in that fashion. That way it's really, really kind of standardized and easy to see. So given our list, where do we set up our left pointer? On the left side, right? So we've set it at the very, very beginning at index 0. And where do we set up our right pointer? Well, you set it at the last index. So in this case, it's going to be right here at index 3. So easy, so simple enough. How do we get the mid index? Well, we know that it's going to be the left, which is 3, minus the right, which is 0, divided by 2. So what's 3 minus 0? That's 3. divide that by 2, you get 1. So make sure you know that 3 divided by 2 is 1. It's not 1.5, it's 1, because you have a whole number divided by a whole number. So that's 1 plus 0. And that's how you get the index 1. And that's because we're doing integer division here, okay? Just something to be mindful of. So notice that the middle index is at index 1, which is exactly what it prints out here. Now, we have to ask ourselves, is the element that the middle index is pointing to, which is 3, is that our target of 5? No, it's not. So what we're going to do is we have to decide, is our target bigger than the middle element, or is our target smaller than the middle element? Well, it's bigger, right? It's bigger than 3. So we want to focus on the right side. We don't want to focus on the left side because those are the smaller values. I know that it should be somewhere on the right-hand side. So now we're only going to focus on here. So what did we say what was our logic if we want to focus on the right-hand side? You keep your right pointer as it is. You don't touch it. You move the left pointer 1 past the mid index. So where would the left pointer move? It would move to index 2 because it's going to be 1 past the mid index. So notice the next step, we're going to have the left pointer right here and the right pointer stays the same. And that's exactly what we have here. And then of course, this is in step 2, where it's going to recalculate the middle index for us. So that's what we're left with here. Now for step 2, we see that our middle index is 5, right? So our middle index is 2, but the element that it's pointing to is 5. Well, that's the same as our target. So remember, we said if the middle element is exactly your target, you found it, you're done. That's a wrap. So that's really it. And that's why we return 2 for this program. So we should be returning 2. And this is, I didn't actually print out the answer at the end, but just know this is going to go ahead and give us the answer. It's going to return the index 2 because we found it. That's why it stops in this case. So let's continue to the next case. And if you don't feel comfortable with this example, please, I strongly recommend kind of rewatching this section. We're going to go through all the test cases and kind of look at it in detail. But let's go to the next case. So now what if my target was 2? I used the same list, but my target was 2. So let's go ahead and set that up. So our target was 2. And let's run it. Then, oh no, let's see. So what we're going to do is, that happens quite a bit sometimes. So we're going to go ahead and reload the page. We're going to paste our code here, just like that. And then we're going to rerun it. That's okay. So here, we're going to go ahead and start back up. So our list is 1, 3, 5, 6 again, and our target is 2. So how do we start off? We know that our left pointer is at the beginning, our right pointer is at the end, and our middle index is at index 1, right? So that's our first case. Now, is our middle element 3? Does that match our target of 2? No, right? Now we have to ask, is the target smaller or is it bigger? Well, in this case, it's smaller. So I don't want to focus on the bigger side like last time. I want to focus on the smaller side, the left side. So in this case, if I want to focus on the left side, I don't move at all the left pointer. I move the right pointer 1 past, right? I move the right pointer 1 to the left of the middle index. So notice this right pointer is going to be moved to here. And that's what we see on the next step. So the left pointer's here, the right pointer's here. And then when we end up calculating the middle index based off of these 2 new left pointers, right pointers, it happens to lie right on top of each other. And that's what happens whenever you have the left and the right on top of each other. Well, the middle's exactly the same place. So now that we kind of see that pattern, we have to decide, is the element that the middle index is pointing to, is the middle element the same as our target of 2? No, it's not, right? So it's not. So what we have to decide, is it smaller or is it bigger? If it was smaller, we'd focus on the left side. If it's bigger, we focus on the right side. Well, in that case, we want to focus on the right side. However, in order to do that, in order to focus on bigger values, the right side, what you do is you keep we keep the right side the same, but what you do is you move the left pointer 1 ahead of the middle, right? You move the left pointer 1 ahead of the middle. So the left pointer is going to go here. And that's what we see below here. The left pointer goes 1 to the right. But remember our while loop. Our while loop is valid while the left is on the left or right directly on top of the right pointer. So if they're on top of each other, this is still valid. Or if the left is to the left of the right pointer, still valid. But as soon as you swap that order where the left is on the right-hand side and the right is on the left-hand side, you're done. That's a wrap. So you know that at this point, you found that the key is not inside of your list. So this is how you go ahead and say, I didn't find it, but I know exactly where to insert it. So this is where you got to like trust me on this, or you got to go just kind of go through examples and see that it works out. Where should I insert it? Where should I insert the target to? So based off of where the left pointer and the right pointer ended, do you want to use the left pointer value or do you want to use the right pointer value? Where do I want to stick the 2? I want to stick it right here. I want to stick the 2 so it's 1, 2, and then 3, 5, 6. So I want to insert it at index 1. So what you're going to do is you're going to return the left pointer. You can return the left pointer, or optionally, you can return the right pointer plus 1. Okay, so that's how that works. So you can either return the left pointer or you can return the right pointer plus 1. And that's what the pseudocode says, right? So at the end, if you don't find it, you return either the left pointer or the right pointer plus 1. And if you go through examples, you'll see that this ends up working out. So that's just something that, through the examples, if you play around with this kind of equation or this algorithm, you'll see that that's the case. So let's go to the next case, which is 1, 3, 5, 6, 7. Let's do that. So let's go through our target of 7. Let's rerun this and let's take a look. So if our target is 7, we already know that left pointer is at the beginning, right pointer is at the end. I'll go through a little bit faster, but just kind of pretty happy with the tool so far. Please like, share, and subscribe if you're enjoying the tool so far. It's it's pretty fun actually, not having to kind of manually scroll, kind of like toggle the values. But anyways, so we'll notice that our middle element is at index 1. Here, the middle element is 3. So our target is greater. So we're going to focus on the right-hand side. In order to do that, we're going to move our left pointer 1 past the mid. So our left is here and our right is here. And that's exactly what we have here in step 2. Our mid gets calculated to be at index 2. So here we have our middle element as 5. Is 5 the value? Nope. Is our target greater than or is it less than the is our target greater than or less than the middle element? It's greater. So we're going to focus just on this right side. So once again, if we focus on the right side, what we're going to do is we're going to move our left pointer 1 past the middle. So that's why we end up having this, the left pointer 1 past the middle, and then left pointer 1 past the middle, which is here. And that's what we see it here. And the right pointer, we don't move it. Now they're all on top of each other. So is the middle element the same as our target? Nope. We still need to go bigger, right? We still need to go to the right. So what we're going to do is we want to move our left pointer 1 past the middle element. And so in order to do that, we're going to have to go out of bounds, as you can see it here. That's what I kind of like about the tool. I'm pretty happy we got to see that example here. So notice it's out of bounds. This was actually a little bit tough to kind of, not tough to write out, but it took me a second to think about it just because, it's kind of out of bounds. Just kind of setting up the IO manip to print it out this way. But anyways, the left pointer is now ahead of the middle index, exactly like we wanted, so we could search the right-hand side. But notice they reversed orders. The left pointer is ahead of the right pointer. They're no longer in the correct order where the left is on the left and the right is on the right, or if they're on top of each other, that's still valid. They swapped. And at that point, we stop the loop. And now you can return the index 4, right? So this is where you would put in the 7. You want to stick in the 7 right here. So when you want it to be 1, 3, 5, 6, 7, so you would do it at index 4, which is what the left pointer is equal to, or you would do it as the right pointer plus 1 in order to say you want to stick it at index 4. It's up to your preference. I just prefer to say return the left pointer just because, I just think it's kind of cleaner rather than having a right pointer plus 1. So hope that made sense. That's really all there is to it. Please let me know if you kind of like this visualization tool. I'm pretty sure there's a lot of other visualization tools out there. I just don't want to be hit with a copyright in these videos. And then also it's kind of nice to show that, we can kind of code our own solutions whenever we come across some problems. But that being said, let's go ahead and go through the implementation. So what's our implementation going to look like? This one's going to be straightforward. We're going to go ahead and set up we're going to set up our left pointer, and we're going to go ahead and set up our right pointer. So left is going to be index 0, right pointer is going to be the last index, right, size -1. And then we're going to have our middle index. Now this one's calculated every iteration. The mid index is calculated every iteration as we update left and right. So when is this valid? This is valid while we said our left pointer is less than or equal to our right pointer. Remember, if they're on top of each other, that's fine. If left is on the left, right is on the right, that's fine. When they swap positions, you get kicked out. Right. Now, what we're going to do is we want to now calculate our mid. So what did we say our mid is equal to? Our mid is equal to our right pointer minus the left pointer. Nope, spelled that wrong. Left pointer. And we're going to go ahead and divide that by 2. And then we're going to add the offset. Don't forget the offset or else you're going to get some logical error. So the next part is going to be these considerations. The simplest one is if your, let's go ahead and set up a value for this. So int middle element, just so that it's a bit cleaner. So what is the middle element? The middle element is just nums at the index mid, right? So that way, if we set up our loop and we say, if the middle element, or let's say if our target equals the middle element. So if there's a match, there is a match. Just go ahead and return that index. Return the mid element or the mid index. Return the mid index where you found the match. Okay. If it's not the case where there's a match, then it's either going to be that your target is greater, in which case we search the right side, or your target smaller, in which case we search the left side. So let's just do greater first, I guess. So if your target is greater than the middle element, there we go. So target is greater, search the right side. So that means what we're going to do is we're going to keep right pointer the same. We're just going to shift left pointer 1 past the middle. Okay, so the way we do that is we go ahead and set up our left pointer. It's equal to the mid plus 1. There we go. And if it's not the case where our target is smaller, so if our target is smaller, we want to go ahead and search the left side. Search the left side. So we're going to keep the left pointer the same because the left pointer is already on the left boundary. We don't want to mess with that, but we do want to shift the right pointer to the left. 1 to the left, 1 to the left of mid. Okay. And the way we kind of write that is we say our right pointer is going to be mid minus 1. So it's going to be to the left of mid. Now, this is going to continue looping, and it's either going to find the value or it's going to break out because, like you saw, it's going to swap sides between the left pointer and right pointer. Last thing we want to do is we have a decision to make. So if we don't get kicked out because we never find the value, we have to return the index where we would insert the value. So you have 2 options. You can insert either number 1, the left pointer, or number 2, you're going to insert the right pointer plus 1. So for this example, I'm just going to go ahead and prefer the left pointer like that. And that's it. That's our binary search algorithm. Really not much to it there. It's like once you kind of understand like the logic behind it, it's pretty hopefully straightforward, I would hope. If not, definitely recommend watching this, kind of reviewing this video. If you have any questions, please feel free to drop them down below. Please let me know if I can kind of do anything to make it a little different. Let me know what you thought about the visualization. Did it help? Did it make it a little bit better? Is it better than my usual kind of manual manipulation of the values? If it is, go ahead and comment below to let me know. But I got to say, I'll be honest, this is the most fun I had making a video. These videos are something that I try to keep very entertaining, or for myself at least. I love learning. And so as I go through the solutions, I'm always kind of having fun. However, whenever I can kind of put a little spin on it, it kind of makes my day. And plus, at the end of the day, what's really nice about these videos is that it really helps me continue to learn, which is really nice. And if it helps you continue to learn too, I'm very happy for that. And that's what I hope to do, and that's why I continue to work as a tutor as well, because I kind of like helping people whenever I can, especially with regards to knowledge, sharing knowledge when I can. But That being said, thank you so much for watching. I really appreciate your patience. I hope you have a wonderful day, and I hope to see you soon.